All right, so this is the last section already in equilibrium. That's why this unit is so quick, and it's going to go by fast. So yesterday I talked about torque. I talked about applying a force that causes rotation. Yusuf, you with us? This is the second time you've been completely zoned out while I'm talking to you. So, yesterday, for a quick lesson, for those who were unwise enough not to watch the video, essentially what I've got is something like this. So, here's a stapler, it can pivot, right? If I apply a force on this, I cause rotation. That's essentially what torque is. The further away from the pivot point, so here's my pivot point, the further away I push, the more torque I have. If I push closer to the center or to the rotation, I have to push harder to rotate. It's the same thing with the door. The reason why the door handle is on the far end away from the pivot point, so that you have to push with less force. That's essentially what torque is. And we talked about a little bit, and I showed an example of the difference between if I'm pushing on an object this way to cause rotation, or if I'm pushing this way. Because if I push here, nothing happens, because I'm pushing into the hinge. And so that's essentially what we're going to talk about today, is that dynamic between what if I'm pushing partially perpendicular, partially parallel. So we're going to get into triangles. So let's take a look at this situation. When I push on it at 90 degrees, the full force causes rotation. If I push at it at an angle, only part of it does. So here is my situation. I've got a sign, here's my uniform beam, and I've got some rope here. So my strategy in going about and solving this is first going to be, let's draw all of the forces acting on this. And I'm just pulling up my set of notes here so that I don't have to do all the calculations, because that'll take a little bit. So essentially what I'm going to do with this is I'm going to draw the beam with all the forces. Now typically you don't have to redraw it. You can draw it on top of there. But I'm going to do it separately just to show you what this looks like. So with this, we've got here some pivot points up against a wall. We've got the beams coming all the way out. We've got the sign at the very end, yeah. I've got the sign is hanging down here. I've got a rope that's hanging over here and connecting to the ceiling. Or something else, I don't know what. So we need to look at what forces are acting on the beam. Not what's acting on the mass, not what's acting on the wall, what forces are acting along this beam here. And we're going to consider this as my pivot point. Remember, the pivot point is arbitrary. I can pick it to be whatever I want, but we can pick that strategically to cancel those out. So here's what I've got. And here, I've got a force due to the gravity of the whatever object is there. We know this value is 100 newtons. I'm just going to leave it like this. And I've got a tension force that's applying here. And what else are we told? We're told that the uniform beam has a mass. So this is Fg from the sign. And we have another force of gravity due to the beam. So these are all the forces that are acting. And notice again, all the forces are acting in different direction, are acting at different points along the beam. So this causes rotation. So if we think about this, if this is my pivot point, I've got Fg of the beams pushing down, I've got Fg of the signs pushing down, and to counter that, I've got tension that's pulling up, but slightly to the right as well. So this tension is going to counteract these two other forces that are acting. Yeah? Because one is due to the sign that's here, hanging on the end, and one's because of the beam. So these are the forces that are acting. I can also talk about the distances here. So I can say from here to here, this is the distance to the beam, because the equation for torque deals with force and the distance. So there's dB, and I've got from here all the way to here. It's both the distance to the sine and to tension, but let's just call this ds to say it's distance to the sine. We know what these values are. Those are given. I know the distance to the sine, it's the full length, so it's 2.2 meters. What would be the distance to the center of gravity of the beam? 1.1. So it's just half. And what else? I can put in other numbers if I want. I can say FGB, we know what that is. We're told it's here. This is 50 newtons. We know the FG of the sine. This is given. It's 100 newtons. Tension's what we're looking for. Yeah. So that's a good question. So is FG of the beam always in the center? If it tells you it's uniform, yes. So uniform means equal density throughout the whole thing. If it's not uniform, I would have to tell you where the center of gravity is. So it's either going to be given in the question or you just assume it's in the center. Wall, ceiling. Coming out of the wall, there's a pole. Attached at the end of a pole is a sign, and there's a rope that's holding it up. Yeah. Yeah. So it's like you've got the wall here, here's the beam sticking out, you've got a rope that's hanging up here, and you're hanging a mast down here. Yeah. And then we're going to find forces on the wall, but we'll get to that later. So notice something with this situation. If we break the tension in the rope into its components, we're only going to have one portion of it that's going to cause rotation. So if we look at this, I can break this up into two parts. I can do this component here, and I can do this component here. So because we want to know parallel and perpendicular, not just x and y, this is going to be t perpendicular, and up here this one's going to be t parallel. So yes, we are again going to use parallel and perpendicular instead of x and y. So if you remember back from inclines, you need to remember this. So the parallel component is not going to contribute to the torque. And we already looked at this, right? We said if I've got my stapler here, if I push towards the hinge, nothing happens. Same thing, if I pull away from the hinge, nothing happens. It's only if I apply perpendicular force do I have movement. So let's go about solving this. Oh, and one other note. I said this, but I'm going to write it down anyways. We're not using ty and tx. So we're not using the x and y components. We must use perpendicular and parallel. Nope. Dynamics, when we're not dealing with inclines, we did x and y. All right. So when we're looking at torque specifically, we need to use the perpendicular component. Perpendicular. So when we're dealing with this, FG, this is going to be perpendicular to my beam. FG again, perpendicular to the beam. Tension, not perpendicular, but I need to use only the perpendicular component. So when we go about solving this, I'm not rotating, so I have rotational equilibrium, which means that my torque in the clockwise direction is equal to the torque in the counterclockwise direction. So I need to balance these two things out. And hopefully by now you're realizing the terrible idea of not watching video from yesterday because I taught this all yesterday. So this should just be review. So from here, what I need to do is I need to look at which forces are causing clockwise rotation and which are causing counterclockwise. So if I taught this trick of using a pen, so put your pen here, put your finger at the pivot point. The forces down are causing clockwise rotation. FG, FG, clockwise. Tension perpendicular is pointing up, causing counterclockwise. So my clockwise rotations are going to be FGB, force of gravity of the beam, times distance to that force, because torque is force times distance, plus FGS, so the force of gravity from the sine, times the distance to that sine. And again, the distance is relative to my pivot point. So all distances need to be relative to my pivot point. So here's my pivot point. Notice each of my distances are from that pivot point. Not from the center of the beam, not from the other edge, always from the pivot. And this is counteracted by T perpendicular times the distance to that point, which is the same as ds. You know, having your backpack in front of your phone doesn't hide the fact that you're on your phone. I know it's instinct for you. But I know instinctively you just reach for your phone every time it dings. Remember the one time when I took it away, you had like 20 notifications in like half an hour. It was annoying me sitting on my desk. Yeah.
So we're looking for tension on tension.
Correct.
And that tension is equal to 0, right?
Correct.
Because it's equilibrium.
Mm-hmm.
And all of this units will be like this.
Mm-hmm. Yep. All the forces are going to add up to 0. All of my net torque is going to equal 0. So really, you only need to remember 3 equations for this unit. F net equals 0, torque net equals 0, and torque equals force times distance. If you know those 3 things, you're good. Plus your Fg equals mg, stuff like that. But everything else you should be good with. Yeah, Jenna? You mean if I drew tension with parallel here and then perpendicular here? So this is a good point, and I'm glad you brought this up. So yes, I could break up my triangle like this. The only issue that I have in setting it up like this is you might think that my perpendicular component here is acting at this point on the beam. But it's not. It's acting here.
What difference? The distance?
Yeah, because it all depends on ds. So I don't show it like this. I always draw perpendicular first to not confuse you. And here it makes sense because, of course, T perpendicular is not acting off the beam. That makes sense. So that's why, in this case, that doesn't really matter. However, if I get rid of this There you go. So if I have something that's acting in the middle of the beam, which if you look at a later question will show up, if I had something that's maybe like this, my T perpendicular is acting here. However, if I drew my triangle like this, you might be tempted to think it's acting here. So yes, you can set it up however you want. You just need to always remember where that force is acting. That's why I always do the perpendicular first in this case. Yeah.
So we're gonna use that 30 degrees to find the equals, right?
Yeah. We'll get there. So, I forgot what angle we've got. Okay, so we are told that with this triangle, this computer's old. So this angle here is 30 degrees. So what can you tell me about the angle inside of my triangle that I drew? Yeah, this one's 30. You can use the Z rule to figure that out, or you could use the fact that these two add up to 90. So this one has to be 60. As you like. But it's easier just putting that as 30. Yusuf, did you have a question? Oh, yes. So torque is also the same thing as what they use with cars. We talked about this a bit yesterday, but torque with cars is how much force the wheels can apply on the road based on the diameter or radius of your car wheel. Yeah, because it's able to apply more force at a given distance from that pivot point. So now we can go through and solve our equation. So let's plug in some numbers. FGB, we know that value, that's 50, times the distance to that point, which is 1.1, plus FGS, which is 100. Again, we're given that. The distance to the sign, we already established as 2.2, equals T perpendicular. So we don't want T perpendicular. It doesn't ask us for T perpendicular, we want T. So let's change this for T. So if I'm dealing with that, here's T perpendicular. And if I want to do that, I'm going to take the hypotenuse, T, times sine 30, because it's the opposite side of that. So T times sine 30, that gives us T perpendicular, times ds. So the distance to where the tension acts is the same as the sine. From here, algebra. I'll get to your question in a sec. Let me finish this off. So in solving this, my tension is 250 newtons. Yeah. Which part's confusing?
The second to last
Which part of it?
the right side.
T sine 30? So if here's my triangle, if this is T perpendicular, this is 30, here's a right angle. If I want to write this in terms of T, I'll go sine 30 is equal to the opposite over the hypotenuse. Solve for T perpendicular. No, and that's what we're solving for. t times sine 30 is equal to t perpendicular. Not sine 30 by itself. So I substituted in for t perpendicular this equation. Because I wanted to solve for t. Because you're adding another 4 steps as opposed to doing it in 1. So yes, you could do that. You could solve for t perpendicular, then from there solve for t parallel, and then Pythagoras t. Too many steps. It's just going to add more to your process. So again, all we're doing, taking the stuff from yesterday, putting in a sine 30. Yesterday, all it was the same situation with t pointing straight up. Now we just added a triangle. Just like we keep doing, we take stuff from last year, add a triangle. You are doing twice as much work today because you didn't watch yesterday's video. Greek letter tau. Tau. Like cow with a T. Tau. No, because that's tension. Or time. How does this look like a W? Do a tilde, an approximate, equate this, and then backwards J. It's not too bad. You'll do enough practice problems, you'll get lots of practice with doing this. All right, so part B is asking what are the vertical and horizontal components of the supporting force on the hinge. So we strategically chose this point as our pivot because I didn't want to know what the forces acting here are. However, if I think about this just logically, if I've got a force of gravity here, a force of gravity here, tension pulling this way, what happens if there's no force here? It's going to fall. Right? You've got all this weight pulling it down. Of course, this is going to sway down like this. So therefore, there must be some forces acting at this point. At this point, you can try and get, or not guess, you can make an educated guess as to the direction of the forces here. So either the force Y is up or down, the force X is left or right. Intuitively, we can try and guess. If you end up with a negative answer, just means you picked the wrong direction. So this is a nice case, it doesn't really matter. But we can try and think about this. So if we said this beam's going to fall down, what direction must the Y force be? Up. So we'll say Fy upwards. Any guesses about f of x? Or fx, not f of x. You think it'll go left? Why? Yeah, sure. Let's try it. Don't spend forever trying to figure this out. Let's just do it this way. So there's two ways I could go about solving this. One of them is easier, and that's the way I'm going to do it. So what I could do is I could set this as my pivot point, because it's arbitrary, and then figure out Fy, but why bother? It's easier to say forces up equal forces down, and forces left equal forces right. That's the lesson you took. That was the one you guys did. So that one's going to be easier for f of x and f of y. We just need to deal with forces up equal forces down, and I need to deal with forces left equal forces right. And then we're good. So forces up, I've got Fy. What else do I have as a force up? Yeah. And my forces down, that's just Fg of the beam plus the force of gravity of the sign. We have all these, yeah. So Fy plus, I don't technically know what this is yet, but I already established what it is here. So it's just 250 times sine 30. Sine 30 is a half, so it's just going to be 125. FGB, I think it was 50, right? Plus 100. Do math, you get numbers. It's 25. Don't forget newtons. Now, notice we assumed correct. And we assumed correct because I got a positive answer. If you ended up with a negative, what I want you to do is just write, after you got the negative, put 25 newtons down, or in the opposite direction. So don't go back, don't go and change this part, and then change your equation again. I don't want you to waste time with that. Just tell me you know what that negative means. Just showing your answer, it means the other direction. So we'll do the same with forces left and right. We assumed force left, right? Yep, okay. So we said f of x equals force right is t parallel. Notice our t parallel is pointing to the right. So Ali made a good guess. So these will equal each other. This is going to be t cos 30. Again, just check out the triangle. You'll see this is true. And this is 217 newtons. So notice with this, it did not ask for what's the total force by the wall. It asked for the components. Exactly. So just be aware, if this says, what is the force on the hinge? It wants the total. Which means, take this, Pythagoras, figure out the angle. That one you're pretty good with. But it's easier just having this figured out. So the unit will change to Newton meters if I'm asking for the torque. So everything I've asked for here is just the force. But if I say, what is the torque caused by the beam? Then it would be Newton meters. So it just depends on what you're asked. How many more questions I got? I got 2. I think I'll probably just do 1 though. Because the other one's the same. Okay. This? No. Instead of it being like this, it's like this. So rule not to break lest ye be broken. And by broken I mean you'll lose lots of marks. So when we find the torque acting on a body, so on the beam, on the pole, on whatever we're dealing with, we must always use the component of the force that is perpendicular to the beam. So yes, I've stated this many times. Now it's in a nice box that hopefully highlights it for you so that you won't forget it. So because of this, we can have funky systems like this, where I now have the beam is not at 90 degrees to whatever the wall is. So the tricky part now is the fact that FG has 2 components. But this shouldn't freak you out, because you've already seen this with inclines. But yet, somehow, inevitably, it always does manage to freak students out. So we are getting to the pinnacle of the difficulty in this unit. The other 2 sections, not too bad. This is where Yes, it may seem overwhelming because as you'll see with the last one, we're going to have a lot of triangles on here, but you can do it. It's going to be good. So let's start off with our strategy. Let's draw all the forces first and then deal with the rest of this. So all we want to know is the tension on the rope. As with the last question, let's just pick this as our pivot point because it's going to make our lives easier. I don't care about the forces acting at that point, so we'll just do this. Yeah?
You chose another pivot point.
Yes. Because if I picked, say, this as my pivot point, I'm going to have two unknowns. I don't know tension here. I don't know the forces here. If I were to pick this as my pivot point, sure, I've eliminated tension because the distance from the pivot point to the tension is 0. And I can solve for this, but why would I do that? I don't need it. So only if I'm asked for what the force is here do I want to do something like that. So it's strategic to pick your pivot point to try and get something that I don't want or I don't care. In the video yesterday, I think the last example I picked, I showed how we use that point strategically to help solve the equation. So that's closer to the end of the video, at least watch that part. Let's draw forces. So what forces do I have in this situation? For the beam? Yeah. So it doesn't say that it's uniform, so we're just going to assume it's in the center. So we've got FG beam. What else do we got? We got tension. It's already labeled and everything for us. So we want to solve for tension. Is there any other forces? No, nothing's hanging, thank goodness. Okay, so we can deal with this. We need to break these up into components. So as I said before, it's easier to put the perpendicular from the exact points that we're dealing with it. It's just strategically it makes more sense. So I'm going to break this up into FGB perpendicular. Yes, we have a lot of subscripts. And FGB parallel. If this is 32 degrees, any guesses where the other 32 is going to be? This should look very familiar from inclines. This one. Right? Always with the perpendicular there. And then with our tension, we're going to split this up as well. So we got T perpendicular, T parallel. The T is going straight up, yeah. But remember, it's only the perpendicular to the beam component that we want to talk about. And then how about with this one? Any guesses where it's going to be here? Where is my 32 degrees going to be in this one? On the bottom. There's a whole lot of calculation I can show with this. So Z rule gives me this as 32. Between the tension straight up and this straight horizontal, this is 90 degrees. And between perpendicular and the beam is 90 degrees. So if this is 32, the rest of this here has to be 90 minus 32. And 90 minus 32 minus 90, which is here, gives you the rest. Yes, but this is not always going to work. Because what happens if I tell you this angle? Then it messes with everything. So you'll need to get a little bit familiar with the triangles. Okay, now this is something we can work with. Because we need to solve for tension. I don't know all the forces, so I can't do forces up, down, left, right. So we need to do torque equation. Torque clockwise equals torque counterclockwise. And again, you can use this fancy pen trick, which I am probably going to see a lot on the test, to figure out what's clockwise, counterclockwise, if you're at all confused. Which of these forces, I've only got two, which of them causes clockwise rotation? Good. So the clockwise is this one pushing it down. So it's F, G, B, perpendicular. That's causing the rotation. Times the distance to that. I didn't label this yet. Just this. It's half of the 1.8. So this is equal to my tension perpendicular times the distance to that tension point. Good so far? Yeah?
We have to draw the distance things on this.
No, you don't have to draw the distance things. That's just for you to see it while I'm teaching it. And to establish, again, it's from the pivot points that we make our distances. Because sometimes they like to try and trick you and say, oh, the distance from here to something over here is this. And you'll be tricked to think, oh, there's a distance already associated with that force, I'm going to put that. So always make sure it's relative to the pivot point. Now let's do some substitution with values I know, because I know the force of gravity of the beam, or I can calculate that because we're given the mass. So this is just force of gravity of the beam times, is it sine or cos in this case? This time it's cos. Cos 32 times dB equals to tension perpendicular. I don't want tension perpendicular. I want the tension total. So this is T cos 32 times dt. That's a value I know. Notice with this, I could cancel out cos 32. It's in all terms. I'm not going to say that you can always do that, because you cannot always do that. But in this case, you can notice that you can do that. Do you need to? No, you don't have to. In fact, if you wanted to, you don't have to substitute in for t first. You can solve for t perpendicular first and then calculate it. You could calculate FGB perpendicular by itself somewhere and just put in a number at this point. That's totally fine. Like if you don't like seeing a huge ugly equation, chunk it and just do step by step. And that's totally fine. I'm more of a plug it all in the calculator at the same time kind of guy. So FGB is just 12, which is the mass, times 9.8, because we're assuming we're on the Earth. Cos 32 times dB, which is half the beam, so 0.9, equals tension cos 32 times the full distance, 1.8, and then solve for t. $58.8. Yeah. Just a sigh of taking it all in.
I understand the light side.
Mm-hmm. Because I just want the perpendicular component here and not the full FG. Because only the perpendicular component causes rotation on an object.
But they're both going in counter. They're both going in a counter.
What's both?
FGD and FGD.
Perpendicular is causing a force into this way, which doesn't cause any rotation.
So that's better.
Yeah, the perpendicular is the one that we're trying to solve for. Yeah, and this one causes clockwise, this one counterclockwise. Mhm. Yeah, so the distance to the tension here is just how far it is along the beam. Yeah, so it's not from here to up here or to the wall. I think someone yesterday asked that too. It's just the distance along the beam. Any other questions with this?
Are we going to do this?
I'm going to draw the diagram for it, but I'm not going to solve it. Once the diagram's made, this part's the easy part. Yes, I know, you're wanting to be very cruel to the other half of the class by trying to make the video as long as possible.
What did you Is this part on the record?
Is this part on record? Of course it is. Same with yesterday's classes on record.
Holiday first? Is it?
Well, no, I had the first, just watch the first 5 minutes of yesterday's video. They wanted to complain about the test because you guys have extra time for the test.
They had a whole week.
Exactly. Okay, so for this, like I said, I'm just going to draw the diagram for this, and then you can go about trying to solve it if you want. But I want to show you again how to set this up, because I think the hardest part is the forces. Once you've got that laid out, the equation part is the easy part. It's trying to understand what's happening in the question first. That's tricky. So let's go about drawing some forces. Actually, I'm going to zoom in here so you can see it a bit better. There we go, nice and big. All right, so forces. So we're told that we've got tension. We've got some mass here. So let's call this FGM for mass. Whoops, let's put this down here. So FG for the mass. We've got some FGB for the beam, and those are the only forces acting. So we're just simply adding one more force on top of what we did last question, and all this is doing, add T perpendicular, T parallel. Add FGM perpendicular, FGM parallel. Add FGB perpendicular, FGB parallel. So all I've really done is just draw the forces, break them into components. Again, the tricky part is, where does this angle lie? Where is the angle in this case? So I told you this is 60. You need to figure out where is the 60 degrees in each of these. The nice thing about this is if you draw it nicely, it's pretty easy to tell the 60 is this one, this one, this one. Because the angles are so clear, you can tell where they are. But if they're not, how could we figure this out? This one? It's not. It's actually the other one. So, everyone remembers the Z rule, right? There's a Z, which tells me this is 60. So if I make another Z, here's a 60. I never draw them, but in my head, this is what I'm picturing. Hey, look. There's a Z. So this is 60. Hey, look, there's another Z. This is 60. Yeah, that's just to make everyone confusing. So the question now becomes, how do I do it up here? Where's the Z?
I know. This. I'm not sure. Like this.
So,
Like this.
so if I want to do this, I would need to do a Z like this. So I'd need to somehow show that this is 60. And how could I do that? Well, we know this is 60, right? What happens if I have two lines that go like this? What can you tell me about this angle? This angle. They're equal. So if this is 60, this one has to be 60.
This one has to be.
Yeah. So there's one way we can talk about it. Ugh, it takes too long to do it that way. Of course, that doesn't work. Perfect. Yep. Okay. So there's another way. What could you tell me? Let's see. So if I have two parallel lines, something intersecting here, what could you tell me about this angle and this angle? Mm-hmm. Well, let's think about this. Hey, look, here's a Z. So this has to be B. Hey, look, here's a straight line with two angles on it. So A and B have to add to 180. So A and B need to add to 180. This and this add to 180. So this gives me 120. And with the 120, I've got this inner angle and 90 degrees. So what's this? If this is 30, what's this? So many tricks you could use with this. This is all stuff in Foundations of Math 11. Exactly. So don't complain, or I don't want to hear any talk about foundations being a dumb math, because I'm tired of that. They learn something that's completely practical for something you don't know how to do. No, it's not. Their Foundations of Math, when I started teaching it, I had to teach myself how to do it first. And it took me, it wasn't, I don't know if I should admit this, but it took me until like second or third year till I actually fully understood it. Foundations of Math 12. No, when I taught it here. You know, it's like the times when teachers have to teach a class that is not their subject area, they have to learn it as they teach it.
Why don't you teach the calculus?
I would love to. There are many classes I would love to teach. You don't want me to teach calculus? Why is that? For the record. Oh, okay. I thought you were giving him a face like, no, don't suggest that he takes over that. I was wondering, why would you ever think such a thing? Okay, so we've established this is 60, this is 60, this is 60. Okay, I'll take you one step further than just this. We'll do the equation. And then from there, you guys can do the rest. So as with anything else, torque clockwise equals torque counterclockwise. Did any of you actually watch the full video yesterday? You didn't watch a single one? Jenna did. Did you catch my reference to a joke that? Okay. Yeah, I told them afterwards. Maybe I'll tell you guys afterwards too. Okay, so once we've established this, I now just need to figure out what's clockwise and what's counterclockwise. Again, we picked this as our pivot. It's just a natural pivot. So use your fancy pen rule, pen trick. What's going to be clockwise? This causes it to go clockwise. Anything this way, counterclockwise. So T clockwise is going to be just simply tension, perpendicular. It's going to be the full distance, so the distance to, let's just see tension this time. Why not? And then the other two are in the other direction. So FGM, perpendicular. It's at the end of the beam. I know it doesn't look like it. It should be. So it's the same as DT plus FGB perpendicular times DB. Do they tell you the length of the beam? They just say the weight. Uh-oh.
It says that beam has a weight of 100.
Yeah, so I know FGB, not the perpendicular. How about the distances? We don't have distances. Well, let's think about this. So if I don't have distance, let's call this D for distance. If that's D, what's this? Half of D. So when I plug all those in here, the D's will all cancel. Because dt is d, dt is d, db, half d. All the d's cancel. All the d's cancel. Not the individual dt, dt, db, the d by itself cancels. So this is a common trick. Just like sometimes masses aren't given, d's aren't sometimes given. All right, I'll leave it at there. You can solve it. If you want to know what the answer is, in the end you get the mass of this object is 52. So you can go about trying to solve that.